So in this example, there's a poll that was taken from a sample of smokers. And they asked the question, do you believe that smoking will probably shorten your life or not? Of the 1,010 people in the sample, 848 said yes. So we already know that our sample size, N, here is 1,010. And our successes in this case, success means that they said yes to this question that they were asked. So success is equal to a yes, which is equal to 848 respondents. So the first question, A. Harris called residential telephone numbers at random in an attempt to contact an SRS of smokers. So Harris was trying to create this random sample by just randomly calling phone numbers. And so based on this, what do you know about based on what you know about national sample surveys, what is likely to be the biggest weakness in the survey? So again, they're calling residential phone numbers at random. Well, this doesn't take into account people with no phone numbers. So people who don't have a phone. As well as in this day and age, many people don't have a home phone because they have cell phones. So cell phones have changed this dynamic as well. So because of these two factors, you could say that there is a slight skew or a slight bias in the survey itself, mainly because they're only surveying a subset of that population. But in part B, they just make an assumption that this is an SRS, regardless of what we just talked about. This is considered a pretty random sample of smokers. So next question is, give a 95% confidence interval for the percent of smokers who agree that smoking will probably shorten their lives. So this is 95% confidence. And they're looking for, that margin of error, if you will. So we're going to need to know a few things. Well, first of all, let's talk about what formula are we going to be using for this question. And the answer is we need the margin of error, or M, and this is equal to Z star, which is our critical Z value, times the square root of our p hat, or our sample proportion, times 1 minus that sample proportion over n, or the square. So the whole thing is we get the square root. So we know a couple of things. We know what n is. We know that n here is 1010, but we don't know p hat. But we can calculate p hat simply by plugging that into a formula as well. So I'm just going to do this. So p hat is equal to success over total population. Oops, sorry. And in this case, that is 848, which this is the number of people who responded yes to the question, over the total sample size, which is 1,010. Now, if you do the math on this, and I happen to have a calculator right next to me, and if I do the math on this, 848 divided by 1,010 should give you 0.8396. And we could just say 0.84. Either way, I just get a little bit more accuracy the more decimal places I go out. So that is my p hat. So now I actually know what my p hat is, and so I can plug that in. I know what my n is, so the only other thing I need is my critical z score, And I can get that by using the table that we were given. So here's the table right here. And if I look under 95%, which I'll try to make this table, keep it out of the way here so I can erase these pieces. So if I look at the 95%, because that's the confidence level that I'm looking for, which is right there. And let me just change the color here as well. So that's 95%. And I'm looking for the critical value. So that's this line right here, this row. And so if I follow that down, I get 1.960 is my Z star value. So 1.960 is our Z star. Okay, so now I'm going to just remove this from our screen so that we can keep working this problem. And let me just erase some of this as well, just so we can clean this up. Okay, so now we need to figure out, we need to plug all of these numbers in to figure out our margin of error. So after plugging all these in, I will get M equals Z star, which is 1.960, times the square root of 0.8396 times 1 minus 0.8396 over our sample size, which is 1010. So now we just need to do a little bit of math here. So if I take it step by step here, I'm going to subtract 1 minus the 0.8396, which gives me 0.1604. So this is going to become 0.16, and we'll just say 0.16 at this point because it'll just make the math a little bit easier, over 1010. And again, we're still taking the square root of this whole thing, and we're multiplying it by the 1.960. So now if I take that number and I multiply the 0.16 times the 0.8396, you should get something around 0.135. We'll say we're just doing a little bit more rounding here. 0.135 over 1010. We're still taking the square root and multiplying it by 1.960. And this, again, we're solving for the margin of error. And so now I'll just divide 0.135 by the 1010, and that should give me something in the ballpark of 1.33 times 10 to the minus 4. So it's basically moving the decimal point over to the left 4 places, and that's times 1.960. And now if I take the square root of that number that I got under with the scientific notation, if I take the square root of that, I should get should get 0.12 if I round. So 1.960 times 0.12. And this, if I multiply by 1.960, I should get 0.023. Now, what does this mean? Well, this means that this is actually this number here is the amount of error that I can get with my proportion, my sample proportion. So essentially, what we're saying is, if I have a normal curve representing these sample proportions, and let's say we had p hat here, we initially said that this p hat fell in at 0.8396, 0.8396. So let's say that's 84% here. And this is our original p hat. What we're saying with this margin of error is that we could go roughly 2% in either direction. So we could go 2% this way or 2% this way. So 82% and 86%. And all that's saying is that if I were to take another random sample and I were to, of the same size, and I were to figure out what the sample proportion was for that particular random sample, that I have 95% confidence that it will fall somewhere between 82 and 86%.